Chapter 19 sucks. It's horrible. Okay? The worst I've seen. What are you going to do? Stop complaining. That's what I should. Okay, early chapter 19, hemiacetal cyanohydrins, weak nucleophilic addition. That's going to have to be on your own. It's just a few steps for each. I'm not going to get into it. There's some other things I think that would be better if I address in these 3 videos I'm going to make that are going to go with the one I made earlier. Okay. These 3, those are going to be individual review. Okay. And when I say individual review, that means with somebody else. If that makes sense. Okay. Acetals, imines, enamines, something we've gone over in SI a lot this week. Forming them, not really the hydrolysis reactions reverse. That's going to be the topic of this video. Okay, so when we formed these in SI this week, remember, water leaves every time. So the reverse of that is using water to attack. Okay, hydrolysis, hydro, water, lysis. I'm going to cut, I'm going to attack, I'm going to cleave, I'm going to use water now to break apart rather than have water leave. Okay, so condensation, hydrolysis. And then with that reductive amination, I'm probably not going to get big into this, okay? It should be reviewed from chapter 18. That doesn't mean just skip over it. I'm going to probably put that in the individual review, okay? This video is going to be long enough with these 3. My next video is going to focus on Wolff-Kishner and nitriles. If we look at the learning outcomes and objectives, we're only forming. It says on there, forming Wolff-Kishner. You should expect to know how to form Wolff-Kishner, and then be able to hydrolyze nitriles. Okay, not form them. And then the last video will be on aldol, what we went in class today. And then Monday and Tuesday will be SI study guide. Okay. Okay. This way. Okay, let's start with acetyl groups. Acetyl groups, right? Ethers on the same carbon. They can also be cyclic. Here I don't have a cyclic one. I have imines, so double bond to nitrogen. And then I have my enamines, okay? With all 3 of these, when we formed them, to start out, we needed some type of carbonyl, either a ketone or an aldehyde, okay? So now these are reactants. We're going to use water. We're not going to form water. We're going to use water. Okay. So these are reactants. We're going to use water to then get back to what we began with, our carbonyl groups. Okay. If I look at my reactants and I look at my products, I can see a few things. For example, here, I need to get rid of an oxygen at least. Okay. I can see here I need nitrogen to leave, and here nitrogen has to leave if I want to get back to carbonyl groups. Okay. What makes a good leaving group? Whatever makes a good leaving group, how well can something handle negative charge? Because when we make something leave, there's our leaving group. When we make something leave, our final step is going to be pushing electrons onto that leaving group. So how well can you handle negative charge? What handles negative charge really well is something, and I'll use the examples we've been doing this week, something with positive charge. If I want to make something leave, give it positive charge. That way when I push electrons onto it, it's stable. Okay? So you'll see here, I want a oxygen to leave, protonate it. I want nitrogen to leave, protonate it. If I want nitrogen to leave down here, we're going to protonate it. Okay? Water is going to be our lysing component here, and it's going to be our attacking species. And if we get the right leaving groups and we're attacking with water, we'll end up with our carbonyl products there. I don't know, your book does a horrible job. It's like it assumes you know how to do the reverse reaction. It gives very little on it. And Dr. Andrews, hasn't really had time to go over. So that's what this video is for. Okay? So hydrolysis, water attacking. Let's leave our acetyl group up there. Acetals are acidic, highly acidic. So we're going to use H2SO4 for this. And yeah, we'll have water. Okay. All right. I need to get rid of the leaving group. How am I going to do that? Protonated. Okay. I'm under highly acidic conditions, so I'm going to assume that this is H3O plus 4 and proton transfer. If I remember protonate something and I'm getting lazy, I'm not really drawing the bond there, just getting lazy with that. And technically I should be using double arrows right now because it is reversible. Your book says that, I don't. So, okay. I've made a good leaving group. I know that in my final product, I need a double bonded CO bond, and I need to get rid of a one of these oxygens here. Looking at our structure here, can we do that? Can we do both in one step? Yes, we can. We reform the double bond. Well, I say reform as in like we've already formed a reciprocal, from our ketone there. And there's my leaving group. I gave it a positive charge, now it can leave. Just like with water, just like we'll see with nitrogen. Okay. Left. Oh. Okay. Sweet. Okay. I've identified leaving groups. I can see that I'm very close here to what I need. Okay. It looks like that, right? But I do have a methyl group up here that's sticking off. It's tough to take methyl groups off. It's easy to take hydrogens off. Tough to take methyl groups off. Okay. This is where we are going to get water to come in. Okay. Here is my hydrolysis step. Hydrolysis. Who has electrons and who wants them? That there, and I have my water that attacked, and this carbon here. Okay, cool. I've gotten rid of one of my ether groups that I attached when I formed it. I need to get rid of my other ether group, okay? At the beginning, I said we need to get rid of one of the oxygens. Well, if we get rid of two oxygens and add one, we're effectively getting rid of one. Okay, simplify that there. Okay. I wanted water here. I've added water, and I have a charge, and I can get rid of that charge. In every case, if you have charge that's caused by either deficiency or abundance of protons, do it. If you have charge like this and there's no protons to take off, we're going to leave it. Okay? So at any point, from my understanding, what I've seen so far in chapter 19 is that most trending wise, like if we see charge on there with protons, take them off or add them, depending on if it's negative or positive. Once we then get to a balanced charge, that's when we do stuff like make water leave or add water. Okay, some of those other steps. Maybe even resonance or a base reaction. Get rid of charge first as much as you can. Don't get rid of charge though of like taking a methyl group off. We're not going to be doing that. So here I introduced charge. I took that proton off. Okay, I've gone as far as I can go. Now I'm at charge again. Let me take a proton off. To do that, we're going to use water again. And to make H3O plus in solution makes sense for highly acidic conditions. Hopefully you can see that we're almost done here. My final product needs to have a double bond and I need my ether group to leave. What can I do? How can I have this group leave and have reform maybe a double bond there? Okay. Before we get there though, what makes a good leaving group? We can't have ether go off. We don't want O- in a highly acidic conditions. Okay. That's very nucleophilic and very basic. So to make a good leaving group, what do? Give it a positive charge. And we could get lazy and we could do an intramolecular proton transfer over here, where if we wanted a proton here, it would just take one off of water. But in reality, this is going to be 2 steps. Okay? So there's H3O plus. This is going to protonate so it becomes a good leaving group. So identifying leaving groups is maybe the most important part of all of this. Now I've made a good leaving group. And I can reform, I say reform, I can form the double bond here and kick my other ether off. And when I do that, remember water is just not going to leave on its own. That's going to stay consistent. Double bond, kick that off. And we'll get plus, notice we make alcohol, okay? And alcohol and carbonyls were our reactants to make this, so it makes sense. We're going backwards, we should expect to make alcohols and carbonyls at the end. Last thing here, I want to take a proton off. To do that, let me just use water. Again. And we'll end up with our ketone, our expected product. Okay. Yes, it's backwards. Your book, I think, does a really bad job of showing that. It just like assumes that you can go backwards with this, okay? So, main trends to think about. What makes a good leaving group? What needs to leave? What should my product look like? How can I get there, okay? Ask yourself questions. You can ask yourself that on every single step, okay? Water's not going to leave on its own. We need something to kick that off. And when we run out of charge ideas, like we did over here, it's usually when water is going to attack. Here's our, hydrolysis right there. Okay? I'm actually probably going to stop this video. I'll make another one that just focuses on amines and enamines. That'll go along with this. It should be somewhat similar.